All right. Hello, everyone. Uh, so today I'm going to do the video lecture on our section 5.5, the calorimetry. Again, like a decent amount of stuff in this thermochem chapter. Those of you that had me 2 years ago, some of the stuff is going to look familiar. Um, maybe after a little rust is shaken off or whatever. It was a couple of years ago, and those of you that had me last year, this is some of the stuff we did not get to fourth quarter with all the COVID things going on. So it will be new for some of you. Um, okay, so this is the notes, obviously already with all my um, marks and everything on them. What I'm going to do is there's kind of like three different sections, part of this, parts of this, and there are practice problems that kind of go along with each section. But in order to keep the video somewhat reasonable, I'm going to split it up. I'm going to go through the info on this page and the stuff I have written here on this first, and then I'm going to do a separate video for the sample problems that go along with each section. Okay? All right, so calorimetry. Calorimetry is a measurement of heat flow, in other words, a measurement of energy. A calorimeter is an apparatus that measures heat flow. And there are tons of different types of calorimeters. Okay. Actually, hold on one second. Okay. I wanted to grab this just to show you, this would be an example of a simple calorimeter that is made out of just styrofoam cups. So you've got like a double insulated to help prevent energy and heat transfer. And then you've got like you can create some kind of a lid like this, and then a hole in it. The hole in it would be for the thermometer to measure. And then obviously whatever you had in there that was changing temperature, whatever you'd be measuring. So even something as simple as this is technically like a calorimeter. And then they obviously make like more precise, I guess. There's like like actual calorimeters are like made, produced and made and stuff like that as well. But like this is an example of just like a simple one. All right. All right. So all right. Heat capacity and specific heat. All right. So over here, these marks are the variables. Okay, so heat capacity is marked by a capital C, is a variable capital C. Heat capacity is the amount of energy required to raise the temperature of an object by 1 degree Celsius. Okay. So that's like for a specific amount of a specific object by 1 degree Celsius. Molar heat capacity, which is C sub m, is the heat capacity for 1 mole of a substance. So like the heat capacity up here is for whatever specific sample you have. Okay, is when you would use that. The molar heat capacity is the heat capacity for a specific amount, for 1 mole of the substance, to raise it by 1 degree Celsius. Okay, that's why the 1 degree Celsius is in parentheses here. Specific heat, C sub S, or specific heat capacity, same thing, is the heat capacity of 1 gram of a substance, the amount needed to raise 1 gram by 1 degree Celsius. Okay. So calculating some of these, this is the calorimetry equation, which again, some of you might be familiar with. It's Q equals MCAT is how I say it, because this looks like CAT. It's Q is the heat, M is mass, C sub S is specific heat, and delta T is temperature. Okay, now what I did, so that's the variables for this. This is the equation written out here in words. This is the variables for it. Now, when you use this equation, okay, uh, your um, your this is this is the equation. This is the equation just rearranged to solve for specific heat. So this is the equation arranged to solve for heat for Q. This is the equation rearranged to solve for specific heat. It's just the same equation, just rearranged. Okay. Now, one thing to know is that your delta T, your change in temp, kelvins and degrees Celsius are interchangeable. You don't have to do anything to convert because it's change in. Like 1 degree Kelvin, the amount that 1 degree Kelvin, or one, sorry, I shouldn't say degree, the amount that 1 Kelvin represents is equal to 1 degree Celsius. Okay, they're different numbers on the scale, like 0 degrees Celsius is 273 Kelvin. Okay, but if you go up 1 degree Kelvin, it's also going up 1 degree Celsius. So since this is change in temperature, for the change in, you can actually just swap Celsius and Kelvin for whatever you need. Okay. All right. Be careful with the sign of Q. Okay. Now, the reason I have a 1 here and the yellow highlighted is because I didn't have room to write stuff up here, so I went down here. So this goes with this part of the lecture up here. This is what it means by the sign of Q. When the sample gains heat, your Q is going to be greater than 0 or positive, which means it's going to be endothermic, right? When the sample loses heat, your Q is less than 0 or negative, meaning it's exothermic. Okay. All right. Next part. Constant pressure calorimetry. Sorry, let me get this. There we go. Constant pressure calorimetry. The most common technique is to use atmospheric pressure as the constant pressure. So unless they tell you, you're just going to assume constant pressure and that it's atmospheric pressure, which is essentially 1 atmosphere. Recall from before that delta H, the change in enthalpy, is equal to Q sub P, which is essentially the heat at a constant pressure. The easiest method is to use a coffee cup calorimeter. All right, so this equation is Q of the solution, the heat of the solution, is equal to the specific heat of the solution times the grams of the solution times delta T, which is just this equation up here. So it's the same equation. Again, Q equals MCAT. Okay? But that equals negative Q of the reaction. Okay? Now, notice I have a number 2 with the green highlight here. That's this part down here. Okay? Let me see if I can get both parts on. Oh, there we go. All right. The Q, the heat of the solution, is equal to the negative heat of the reaction because the heat lost by the reaction is gained by the solution and vice versa. This is the concept of the system and the surroundings. Okay. Now, where this gets really sort of I don't know if complicated is the right word. Somewhat complicated, and it can just be a little weird. And that is, let me get another sheet of paper here real quick. Okay. When you have a reaction, okay, so say we have you put 2 aqueous solutions together, okay, and you get a we get a reaction. It doesn't really matter what the reaction is. Let's say we put I don't know, let's see, hydrochloric acid uh, with a solution of sodium hydroxide. So it's a neutralization acid-base reaction. Okay, and this is occurring in uh, in a solution. They mix them together. Okay, so in the solution, you get the reaction, right? You're going to get this reacting um, and you're going to get a salt, right? The aqueous Na, the sodium chloride, and and water. Okay. So this is the reaction that would occur inside, like when you mix the two solutions together. Okay. Now, here's the part for thermodynamics that can seem a little weird. The reaction, the actual reaction itself, is the system. Okay. And the heat of that would be the Q of the reaction. Okay. Now, the surrounding the water, the solvent, is actually the surroundings. Q of the solution. So what happens is you actually get energy transfer between your you get energy transfer between the reaction and the solution. That was supposed to be orange. It's not a very good orange. So you get energy transfer. All right. Now, what this means is because energy can't be created or destroyed, right? So we already know the relationship between system and surroundings. The energy or the heat that the system loses, the surroundings gain, and vice versa. If the surroundings lose energy, the system gains it, right? Okay. The tricky part is understanding that within an aqueous solution mixture that's reacting, the actual reaction, the molecules that are reacting is the system, and the surrounding aqueous solution is the surroundings. So what that means is, like if we have a coffee cup calorimeter like this, and we're taking the temperature, like we mix two things together, right? We're getting a reaction, we're taking the temperature. What we're actually getting the temperature of is the solution, not the reaction. We're actually getting the temperature change of the solution. And because of this relationship, whatever happens to the solution. So if your temperature goes up that you're measuring in that means that the solution is gaining energy, and that means that the reaction is actually losing it. If the temperature goes down, that means that the solution is actually losing energy and the reaction is gaining it. Okay? It can be a little confusing because a lot of times we just think of the liquids themselves as being the reaction. So, okay? All right. Now, the third thing, along with this, remember this is the Q equals MCAT equation. So the blue mark here goes with this equation still also. For these coffee cup calorimeter, regular calorimetry. Oh, let me move it down here. Temperature increase. A temperature increase means the reaction is exothermic. Your Q over your reaction is negative. Okay, this is the temperature increase for the solution. A temperature decrease means the reaction is endothermic. Q of the reaction is greater than 0. Okay. All right. Now, the last thing for this section here, for dilute aqueous solutions, so pretty much the aqueous solutions that we do, the specific heat of the solution, the CS, will be close to that of pure water. So if you're doing a coffee cup calorimetry, like an aqueous solution reaction, thermochemistry, if they don't give you a specific heat, you're going to assume that it's the same as water. Okay, and I've given that to you down here. You need to make sure you write this down for sure, because they're going to assume that you have this memorized, basically. They're not going to always give that to you in every problem. Some problems they do, but some of them they don't, and just assume that you know what the specific heat of water is. So the specific heat of water is 4.184 joules over grams Kelvin, or joules over grams degrees Celsius. Either one can be swapped in there. That's the specific heat of water. Okay. All right. The third section is on what's called bomb calorimetry, or constant volume calorimetry. Reactions can be carried out under conditions of constant volume instead of constant pressure. Constant volume calorimetry is carried out in a bomb calorimeter. So I'm actually gonna, I should have had this pulled up already, but I'm gonna show you a So essentially what a bomb calorimeter is, let's see if we can get one of these images a little, oh, it's not very helpful. Okay, how do I get these bigger? Does not help. Hold on, let me zoom in with my board. I know it fuzzes the info here, but basically all you need to really know is this is a bomb calorimeter. So a bomb calorimeter is, excuse me, a calorimeter where it has some method of combusting, usually through some kind of like electrical means of combusting a substance, burning a substance inside of a closed container. That closed container, that's the constant volume part. Okay, the volume can't change. It's a closed container. That combustion chamber is usually surrounded by water or some other liquid, and the thermometer in that, and so that's considered the surroundings. And then there's another outside insulator to keep the energy transfer from the surrounding air limited. So that's essentially what a bomb calorimeter is. Okay. All right. So, the bomb calorimeter problems have a special equation that goes with them. How will you know it's a bomb calorimeter problem? Well, there's a couple of ways. One, it'll say something out of bomb calorimeter. Okay. Or two, it will give you a heat capacity, and the heat capacity will be oops, sorry. Hold on, I don't have it marked here. I probably should have this marked. So the heat capacity for this in a bomb calorimeter, the label for heat capacity of the bomb calorimeter will be in a like joules or kilojoules, so energy over energy G label over the temp label, temperature label. So for example, like this isn't the only one it could be, but uh, like kilojoules over degrees Celsius. So the thing is that's going to be different from your label for specific heat. Okay, the specific heat label, if you look down here, the specific heat of water will be energy over mass times temperature. So if they give you a heat capacity for the calorimeter, if they say the heat capacity of the calorimeter is, that's a bomb calorimetry problem. Okay, if they give it to you and it's got energy just over temp, that's heat capacity for a calorimeter, which is a bomb calorimeter problem. Okay, so those are all different ways to tell. So the equation for a bomb calorimeter is the Q of the reaction is equal to negative Ccal, the heat capacity of the calorimeter, times delta T, change in temp. Okay? Since the reaction is carried out under constant volume, your Q relates to delta E. That means your Q essentially is your delta E. Because no work is being done, because nothing's moving, because the volume stays the same. Okay. All right. That's it for the explanation, for the walkthrough of this. Like I said, I'm gonna do some sample problems. Sorry, for each section or for each part of this. We'll do those in a different lecture. All right. As usual, if you guys have questions or need help with anything, let me know.